In the last video, we were looking at evaluating line integrals of a vector field, which we saw is not all that different from a scalar field. In this video, we want to look at an example of this, and specifically, we want to look at an application type of example where we're considering the work done by some force. Now, even if you haven't done physics before, you can think of work as just being the integral function of force. So really, it's an application question, but you don't really need to know any physics in order to do this. So let's break this down piece by piece. So we want to find the work done by this force that's given to us as 9xy in the I direction and 6y squared in the j direction, acting along the piecewise smooth curve. So here we have a piecewise smooth curve. And I'll explain to you why this is not really that much difficult or more difficult. So that curve consists of the line segments -2, 2 to 0, 0, and then from 0, 0 to 2, 6. So this might be very confusing at first, and you might be thinking that we never even talked about how to do this. But you'll realize this is not really that much different from what we've been talking about. So when it's giving us these 4 points here, it's essentially describing to us the curve C that's in our line integral. But usually we want C to be in a function form, and that's not a problem because it tells us here that C is a piecewise smooth curve with 2 line segments. We have one line segment here from -2 and 2 to 0, 0, and then after that line segment, then we have this new one. So how do we generate the curve? Well, we know it's a line segment, so we all know that it has to have the form y equals mx plus b. Now let's just think of the slope. To do this, we want to look at the change in the y direction over the change in the x direction. So let's do 0 minus 2, and that should be 0 minus -2. So we'll have -2 divided by 2, which is -1. We can do the same thing over here, but instead we'll have 6 minus 0 and 2 minus 0. And so we get 3. And now I don't really need to worry about the b part, the y-intercept, because it's telling us that whatever line we're talking about shares that point 0, 0. So we know that there is no y, the y-intercept rather is 0. So here we'll just have y equals minus x, and here we have y equals 3x. So here, instead of just giving us one nice function for the curve C, the curve C can't be described with just one function because it's a piecewise smooth curve. So the first part of it is equal the y equals minus x part. Then, where that finishes at 0, 0, the curve then continues, but along a new line segment, y equals 3x. And this is perfectly okay for us, because as you remember, we're doing integration. And so even though we have a different function, we can just split that integration. We don't need to go all the way from -2 to 2, for example. We can split that. And I'll show you what I mean by that. So before we get too far into this, let's just figure out what we know. So we have two equations that are describing the curve C to us. So we have to look at each of them individually. So first we want to write this first one parametrically. So for example, we might say x of t equals t, and if x and t are the same thing, then y of t must be equal to minus t. For the other one here, you can do the similar trick. We'll say x is just t, so y of t would be 3t. Nothing new really so far. Now, remember, we're trying to integrate here with dr, and dr is the derivative of all of these components of the curve C. So I can write it out so it's very clear. X prime of t is going to be 1, y prime of t is going to be -1, and so therefore for the first part here, we have that r prime of t is 1, -1, and here we'll have x prime of t is 1, and y prime of t is going to be 3, and again, we'll have here 1, 3. Now I know I'm using the same variables here, but you have to remember that these, all the x's on the left here and all the y's on the left and the r, and the ones on the right, they're not really the same thing. They're continuations of each other. So first we're going to be using this r prime of t on the left, and then we're going to move into the one on the right. Right now it's very abstract, but don't worry, we'll see very shortly how it all comes together nicely. The other thing here that's very important is we have to think about our bounds. So again, as we were looking at an example before, they gave us a lot of different points here, which we did need in this question because we had to actually find the equation. But when we're talking about the bounds, we don't need all those points. We just want to have bounds in terms of t. Now again, it's very nice for us because in both cases, we have x just equaling t. So the t bounds can essentially just be the x bounds, which in this case is just going to be minus 2 to 0. And here t is going to then go from 0 to t. So overall, we are integrating the function f, the vector function f, from minus 2 to 2, but we can't do it all together because we have two different functions. So let's put this all together. So we're going to have two pieces here. So first, let's integrate from minus 2 to 0. Now what am I going to put here? I want to put the vector function f as it's given, but I want it evaluated at x of t and y of t. So the first component here is 9xy. Okay, so we have 9. Now what is x? X is just t. And what is y? Y is minus t. That's the first component we took care of, the 9xy. Secondly, we have 6y squared. So we'll have here 6y is minus t squared. And so that's going to be the f part. And then remember we want to dot that with dr. And what is dr? Well, dr is just the r prime of t dt. And we're talking about the first function here, so we're going to use the one on the left here, which is 1 minus 1. And then we have dt. Now, I don't have all that much space here, so I'm going to do them separately, but you can then continue and add on to it the second integration, but we'll do that part after. So now this is very simple. We just want to do the dot product, simplify, and then we'll integrate. So let's go through that. So minus 2 and 0. Here we're going to have minus 9t squared and 6t squared, dotting that with 1 and minus 1. And the dt. And when we do that dot product, we are going to get minus 9t squared. And we are going to be adding the negative 1 multiplied by the 6t squared, or just having minus 6t squared dt. And now again, this is a very simple function to integrate. Let's do that. So what do we have here? Well, we want to increase the exponent there to t to the 3, and then divide by 3, so we'll have negative 3 t to the 3, and then over here, we're going to have minus 2 t to the 3. And actually, let me correct myself, because there was no need to do that. We have the same function here, or the same variable actually, so before we do that, this is actually a good habit to get into, you should combine them. This is just minus 15 t squared. And that would be a better way of doing it actually, because then you can avoid any mistakes. So let's carry on. So we want to integrate this. So we're going to have minus 5, the minus 15 divided by 3, t to the 3, and we're going to evaluate that from minus 2 to 0. So we'll now just work that out. So we have here, we'll have minus 5, and we'll have 0 cubed. Then we're going to subtract, and here we'll have minus 5 multiplied by minus 2 cubed. So the first part there is just 0. Then we have minus 5 times minus 8, which is 40. Then we have the other negative, so we'll get minus 40. Now we're not done yet. We still have to do the second part of that integral. So right now we just finished this first portion before 0, 0. Now we need to do the second portion after 0, 0. So this is y equals 3x. We want to do that portion next. However, it's essentially the same thing, so we'll just go through that quickly. So now we're going to integrate from 0 to 2. Remember, those are the bounds on t. If you put in the values of x of t and y of t into that vector function f, we will get this. Again, I'm going to skip a few steps just to go through it a bit quicker, but it's identical to what we did earlier. We want to dot that now with r prime of t, which here is 1 and 3, 1 comma 3. And then we have dt. Now we just want to do the dot product between those. So we will get 27 t squared plus 162 t squared dt. And now it's just a simple integral that we can easily do. But first, actually, before we do that, let's combine the terms to make it even easier. So 0 to 189 t squared dt. And now let's do the integral. So we will get 189 divided by 3 t cubed. And that's going from 0 to 2. Let's work that out. So we don't need to worry about the 0 part because that will go away. So we'll just do the first part, 189 over 3 t cubed. And so now we could work out the number here, but we don't really need to right now. We have this portion of the curve. We found the integral, and we have this portion, the minus 40. And so now we finished the two segments. We have the first line segment and the second line segment. Now we just have to add them together because we want the whole thing. We don't want them in pieces. So let's do that. Minus 40, adding to that 189 over 3 t cubed. And so again, just to make that very clear, this is from the first part, that's from the second part. If you work that out, you'll get 464. And that's the answer here. So again, there's a lot of places that you can make small mistakes, but if you take it piece by piece, it ends up not being that bad. The only real tricky part here perhaps was that you have to realize that the curve C is not really given as nice as we'd like it. We kind of have to figure that out. But I hope you see that it's actually not that bad. So that's it for this video.